Hey, good afternoon, class. Mr. Bean here. I've been asked to give some hints on Lab 54 conservation of energy simulations. All right, so kind of give some hints here, maybe how to do some of these, and let's go ahead and kind of see what we got going on. All right, so I'm going to go ahead and start with energy on a toss. So let's take a look at it and kind of see what's happening. Okay. Go ahead and take a read this here and see what the situation is. So energy on a vertical toss. We'll click begin here. And it says use the ideas of energy conservation to find the total energy of the system and the height that the ball will reach based on the conditions that are presented to you below. All right, so taking a look here, we have, looks like, let me go ahead and get some drawing tools here. Okay, so we have a ball here that's going to go up to the top. So we'll start with some kinetic energy. Okay, so let's kind of draw it over here. Let's kind of draw a surface here. Here's this ball. Okay, so it starts off with some kinetic energy. Okay, and it's going to go up to the top, and then somewhere up here it's going to come to rest, right? So up here, V is going to equal 0 um, at some point, and when V equals 0, it's going to be kinetic energy here is going to be 0, and this is going to be looks like 100% potential energy. Okay, at the bottom here, when it takes off, it looks like the kinetic energy is going to be 100%. Okay, and the potential energy is going to be 0. Okay, 0%. All right, so we'll do our conservation of energy here, and let's kind of see what's going on here. So we have potential energy initial plus kinetic energy initial minus any work done by friction will go here is equal to final potential energy plus the final kinetic energy. So looking at this here, what's going to be, okay, well, let's plug in what's going to be 0. Initial, this is going to be 0. Initial potential energy is 0. There's no work done by friction, and the final work or final kinetic energy is going to be 0. Okay, so the kinetic energy here we should know is going to be 1/2 mv squared, like so. All right, so that's kinetic energy, and this is going to be the final, that's going to all be converted into final potential energy at the top. Okay, so here's our, so the total energy is basically right here. This is it. So our starting kinetic energy, whatever it is going to be our total energy. So it's in here, total energy. Okay, energy. Okay, that's going to be our total energy. Okay, energy, total energy. All right, so this is going to be U. So whatever this turns out to be is going to equal our final potential energy. Okay, now once we have our final potential energy, we can use mgh to figure out what the maximum height should be. Okay, now be careful, this is in centimeters. Okay, so we want to be very careful here that we do the conversions. All right, this is simulation number 1. I'll go ahead and hit pause. Okay, next up is we have simulation number 2, energy on an incline level 1. Let's go ahead and take a look at it and see what we have going on. Okay. All right, so go ahead and take a read this here. Remember, the cart by itself has a mass of 500 grams. Okay, all right, we'll go ahead and click on begin. All right, so ignoring friction, use the idea of energy conservation to find the distance the cart will travel along the incline based on the conditions that are presented to you below. The cart, the mass of the cart itself, without the mass on top of it, is 500 grams. Okay, so let's take a quick look here and see what we got going on. All right, so essentially, this has some initial speed here of 2.807 meters per second. All right, so it's going to fire, it's going to come up, so it's all kinetic energy. Now it's going to go up the ramp here and come to rest at some point up here, right? Okay, so we want to use conservation of energy and not use the kinematic equations. Okay, so the conservation of energy, let's go and take a look at it and see what we got. We have potential energy initial plus kinetic energy initial minus any work done by friction. We'll go here. Let me get an eraser and let's erase this here. Okay, and it's going to equal the final potential energy plus the final kinetic energy. All right, so this cart starts moving. It's going to come to rest at some point up here. Okay, all right, so what's going to be zero? Well, it starts at the bottom here, so we're going to say zero potential energy. There's no work done by friction, and there's no kinetic energy at the end. All right, so it looks like it starts off with some kinetic energy. All right, so this is going to be, let's take a quick look here and see what we got going on. So we have here, looks like 1/2, right, mv squared, okay, equals here, this is going to be mgh. All right, now over here, there is no h over here, but if I do remember, this looks like a triangle, right? This is the side opposite. Here's the hypotenuse here, and this is an angle. So let's go ahead and take a look at that more closely and see what we have going on. So we'll call this distance d here, okay? And of course, here's theta, and this here, this is angle theta, and this is h. Okay, so the relationship here is sine of theta, right, is equal to, let's take a look here, it's going to be the height over d. Okay, now there is no h here, right? So let's take a look here. Let me solve this for h. If I solve this for h, I'll get d sine of theta here is equal to h. So this is my ticket right here. Plus, I also want to find the distance it travels up the ramp. So if I go over here, I'll have 1/2 mv squared, right, is equal to mg, and we'll do the substitution. There's d sine of theta. So I think you should be able to solve for d here from here. All right, that'll be some hints on simulation number 2. All right, simulation number 3, energy of a displaced pendulum. So let's go and take a look at this one here. All right, okay, so here we have, we'll go ahead and begin here. Okay, so here we have this string here, mass and starting angle and g. Find the speed of the pendulum bob when it reaches its lowest point of the swing. All right, so we'll go over here and take a look at it. So it's here, and it's going to take this path like this here. And this will be the bottom right here. And here we have this here. This kind of like make it a little bit longer. There we go. All right, so this is our angle theta here. Okay, this right here. Now here in this position here, starting from rest, so this is going to be all potential energy. Okay, this is going to be 100% potential energy. No kinetic energy. Okay, kinetic energy is going to be 0. At the bottom here, okay, it's going to go in this direction here. Potential energy is going to be 0, and kinetic energy is going to be 100%. All right, so let's take a look here and see what we got here. So how do I describe this potential energy up here? So potential energy is usually given as mgh. Now, because we're not given height directly, we do know the length of the string. That is given. Okay, now it's in centimeters. Got to be careful. And this is in grams, so make sure we're very careful here. Okay, so we do know that h, we showed this in class, that h is really L times 1 minus cosine of theta, like so. Okay, that's our substitution here. And so what we have here then is I have the starting potential energy plus starting kinetic energy minus any work done by friction is equal to the final potential plus the final kinetic. Okay, so at the bottom is all kinetic energy, so that's 0. It starts from rest, that's 0, there's no friction. So this is going to be mgh is equal to 1/2 mv squared, like so. All right, so So we should be able to calculate, some things here. Maybe, I think they want you to calculate the energy first. So we will get it from here, MgHO. This would be HO here, and this is going to be mg, and it's going to be L 1 minus cosine of theta, like so. Parenthesis equals 1/2. Here's mv squared. All right, so from here, we should be able to solve some things here. All right, there's your hint for that. I'll go ahead and hit pause.